standing in the defendant box, so I'm gonna defend this way. Okay. uh, Good morning again, and thank you for being here, especially the audience. As speakers, we have to be here, but as audience, as Raphael said, you'll get a medal from him, you get a beer from me. So, I am part of the Department of Building Construction, College of Engineering at Virginia Tech. Virginia Tech, if you don't know, is in Virginia, where the main campus is in Southwest Virginia. We also have starting a huge campus in Northern Virginia outside the Washington, D.C. area, supported by the Amazon funding that came over $1 billion that's coming over 10 years. So we're excited about that. I want to recognize my co-authors. My first author is Akhil Yanamala. He's from India, and he's finishing his master's degree in civil engineering. And the second author is Ashit, Harode, also from India, and he's almost complete with his PhD. And the work that I'm presenting today is really culmination of work that we've been doing for the past year with the support of these guys. My research objective and also my table of contents is three components of my title: a system-centric, ontology, graph-based digital twin. And I'll address each part of those three components of the title as I go in the presentation. The work is applied to an actual facility. It's a two-story middle school, a lower school, middle school out of state of Maryland that we used as the test case study. The work is applied to the mechanical system in the building, just the mechanical system, and specifically to a specific zone, that what we call Zone 4. So we analyzed the building mechanically. We identified 4 zones. Each zone is actually supported by a different configuration of the mechanical system. Zone 4 included the gymnasium and supporting rooms highlighted in green. And we focused on the mechanical system for that zone. Okay? That's the case study. The first part of my title is system-centric. The term system-centric is not new. It's been in the literature. It was in Raphael's book as a case study. It's how facility managers perceive and want to review and navigate and analyze building models. They look at it from a systems perspective, how components of a specific systems are connected. This is important to facility managers because when they are performing a maintenance task or an emergency operating task, they have to look at the interconnected systems. Not only that, but also what department or building zone that impact is, who are impacted. If I'm a researcher that have a lab and the system is down, they want to know who that individual is. So all this could be achieved by defining specific parameters, specific properties in the model or in the graph in this case, that would allow you to search and navigate and analyze and query the model or query the graph from a system perspective. Okay? So we created a set of parameters that allows us to do that. Some may argue, what about BIS? BIS tells you where the fault is, but it doesn't tell you the location. And so by doing a system-centric analysis of the model, we can identify the location of the fault. We can determine what systems and subsystems are impacted. We can determine what personnel we have to notify. And we can also determine the size of the zone or the space in the building that is impacted by that issue. So a system-centric analysis of the model is really critical. In our definition of data, in our classification of data, we looked at static data versus dynamic data. Dynamic data is not addressed in this research. We focus on static data, specifically asset identification properties and system-centric parameters. These are the parameters that we define and built into our graph with values to allow us to analyze the graph and query the graph from a system perspective, okay? One of the tedious tasks that we had to do is we actually had to go into the mechanical system for zone 4 for that gymnasium and actually provide a unique ID for every component so that the graph can actually represent the model. So we're relying here on the graph to be a representation of what the model is. So we went in for every component of the ducts, the equipment, and all the supporting elements of the mechanical system and provided it with a unique ID, user-defined unique ID. And many times we relied on the ID number provided in the 2D plans for the project. The second part of our title is a ontology for a graph-based. We wanted to explore the use of graph databases to represent 3D models. So we focus on LPG type of a graph. In fact, we used a off-the-shelf platform called Neo4j. You're probably familiar with it. We defined component of the mechanical system using nodes and relationships, and we attached different properties to the nodes or to the relationships. That's how we represented the graph. We defined our own ontology with some references to what others have been using. We represented assets and spaces as nodes. We represented relationship between assets and spaces using specific defined relationships. For example, I don't know if there's a pointer in here, but for example, if you look at the top right, an asset is embedded in another asset. For example, you have a fan that is embedded in a rooftop unit. So that's how we represented the model using the graph. The list of 16 parameters that we used in the graph is on the left-hand side, and in the blue, it shows you whether this was represented as a node label, or a node property, or a relationship property. Just to give you an idea about our graph, we ended up creating 5 large subgraphs on the left. We use a product called Arrows, which is a subset of Neo4j. You can actually graphically create the graph instead of typing it. And then we use cipher code to combine the 5 large models, graph models, into a single model inside Neo4j. The reason we did that is we wanted to do some quality control of what we're doing. So by breaking down the final graph initially into 5 different graphs, for example, the supply air was a graph, the return air and exhaust air was another graph, and so on. Just from a quality control perspective. We obviously could have created the entire graph all at once, but we chose to do it that way. This is an example of a subset graph from the entire graph at the end. It represents mechanical equipment connected to ducts that are connected to other electrical equipment, to panels, to circuits, and so forth. Obviously, you can't see it from here because of the quality of the slide, the projector, but you can see some of the parameters that are already attached to each of the nodes or the relationships. This is my favorite part. We inserted the term digital twin in our title, and this is one of the reviewer's comments. He was not happy that we called the title was digital twin because the information in the model was only static, which he said, which is completely fine, but that is not related to digital twin, is it? And here's my response, and I responded to the reviewer respectfully. We don't know what a digital twin is, right? Not yet. Everybody is calling it digital twin. Anything that is on your computer, it's a digital twin. Very interestingly, a couple of companies, Magellan and forgot the name of the other company, did a huge videography of the Titanic last summer, and they released the videos recently. All they did is scan the Titanic. They used over 700,000 pictures that were stitched together, very detailed. And the CNN, BBC, many of the big news companies, they advertise that as the Titanic digital twin. It is basically a 3D model with no data in it yet. I don't know what's going to happen, but it's advertised as digital twin. So a big part of the world, think of digital twin is anything that moves like that and gives you details of what the actual thing is. On the opposite side of the spectrum of what we think digital twin is an article that I wrote, that I read in the Times newspaper about Apollo 13 and how the fact that the ground crew communicated with the ship for over 3 days trying to respond to what the information coming from that ship is, and using that information to simulate multiple scenarios to allow that ship to come home. And what the article said is that I have to have a physical to be a digital twin. The digital twin has to be connected to that physical. It has to be adaptable, meaning if that physical conditions change, the digital twin has to react to that. And it has to be threaded, with what we call a modular digital twin. We can't create a digital twin of a city by creating a single digital twin. We have to build the digital twin of a city using multiple digital twins. Quickly to wrap up, we tested several scenarios to search the graph. This is an example of a situation where the facility manager needs to know where the mechanical equipment is connected to what panel, to what circuit, so that I would know where it is so I can actually go shut it down in case of an emergency. We use also Neo4j Bloom allows you to actually save the searches, so you can provide that graph as a product to a facility management department with all the searches possible, saved as a search number, and all they have to do is just click on it. So Bloom allows you to do that. We also, I'm going to jump through here, we also created a workflow to allow us to go back to the model. In this case, the model was in Navisworks, and allow us to identify objects in the Navisworks model that were queried in the graph. So that allows us to go back to Navisworks and show what are the components of the query in the model. I'm going to skip my discussion, and thank you for listening.